If you clicked on this video, you're probably familiar with Tic-Tac-Toe. You have a grid of 9 squares, and players take turns placing X's and O's until one of them gets 3 in a row, or more likely than not, you'd run out of spaces and the game is a tie. Unless, of course, you're a cat. Well played. It's easy to imagine pushing this into 3 dimensions. You stack 3 boards on top of each other and get 27 cube-shaped spaces, though we quickly find that on this 3x3x3 grid, X is basically always going to set up a win on their third move, unless you modify the rules somehow. But what would it take to push this game into 4 dimensions, and is there a way to make it worth playing? Usually, we try to visualize a 4th spatial dimension using a projection. I've set this 4D board rotating so we can see it from different angles, but it looks a little weird. The cells seem to stretch, distort, and overlap inside each other. It's important to understand that this isn't because the shape itself is changing, but because parts of the shape are pointing in a direction that we can't observe from our current vantage point. This is exactly what happens when we look at the 2-dimensional shadow of a 3-dimensional object. As the object turns, squares squash into flat lines and angles seem to shift, even though the shape itself hasn't changed. So we have our 4D tic-tac-toe board, but this particular version is a confusing shadow, and it seems pretty impossible to play. And that's before we deal with the fact that O has absolutely no hope of winning. There are a lot of ways to solve these problems, but in particular, we'll talk about a version of this game you might have actually played before. But what is a dimension anyway? In a non-rigorous sense, we can describe a dimension as a unique or independent direction. Imagine having an arrow, what some people might call a vector, that moves in a specified direction. We can scale it up, scale it down, add them, or even subtract them, but all of the points we end up with will be on the same line. That direction is our one dimension. Whatever we do, we can't use that dimension to get off of our line onto other parts of our 2-dimensional screen. We can introduce another direction, another dimension, outside of this line, and suddenly we have all sorts of new opportunities. We can combine vectors from these 2 dimensions to travel all over the screen. In fact, using some combination of these vectors with different scalings, we can get to any point on the infinite 2-dimensional plane they're both sitting on. It's often helpful if we require that our chosen directions are orthogonal, which means arranging them so they are perpendicular to each other. We have one exactly vertical direction, one exactly horizontal direction, and no funky overlap in between them. This often makes thinking about dimensions easier, especially when we have more than 2 or 3. The trick is that a dimension is really just a way to categorize differences, a slider that we can adjust to describe something. I can use some perspective tricks to draw in another direction that looks like it goes into and out of the screen, which is like adding a slider for depth, but we could just as easily move along frames in our video or positions in our hard drive memory, and that's just getting started. Once we realize a dimension is just a category, we aren't limited by space or time. We can move in any direction where data varies. I've been using color to differentiate our dimensions up to this point, but of course, there isn't any inherent color to our spatial dimensions. It doesn't matter how far up, down, left, right, in, out, past, or future you go, you're never going to find your way to green. We can think of color as another dimension that's independent of our spatial coordinates. When we talk about colors in contexts like digital graphics or printed media, we use coordinates that take advantage of how our eyes respond to light. So when we see unique colors on our screen, it's actually a combination of red, green, and blue values. Each color is an independent control channel. Let me show you what I mean. Instead of up, down, and left, right, imagine our horizontal axis is a slider from no green to full green. If we do the same with red on the vertical axis, we can reach all sorts of combinations. But there are many other colors we can't reach unless we add a third blue axis as an additional dimension. Red, green, blue is a convenient way to coordinate color for screens, but our actual vision is messier. Our retinas rely on 3 types of specialized receptors called cones. Unlike a screen pixel that emits light concentrated in narrow wavelength bands, our cones are more like wide nets. Each one catches a broad range of wavelengths, roughly distinct but with a lot of overlap. These broad buckets result in something called metamerism, where different mixtures of light look identical to us, but that's something we'll have to cover another time. What we'll focus on here is that the peaks of these sensors don't line up exactly with pure red, green, and blue. When we use the peaks of the cones as our axes, the resulting dimensions aren't quite 90 degrees apart. It's still the same three-dimensional color space, we can reach the same colors, but we're using a different set of coordinates to get there. Our brains combine these overlapping signals and resolve them into the sharp colors we experience. In fact, our brain is doing this calculation for many points of light hitting the back of our eye. This means typical human vision is actually 5-dimensional. We have 2 spatial dimensions to capture where something is in our field of view, and 3 color dimensions based on how much light is actually detected in each of our 3 cone types. And if you're frantically typing something about rods being an additional dimension, you can pause here for my response. Most mammals, like deer, have only 2 types of working cone cells, which means their vision spans only 2 dimensions, and is similar to that of humans who are red-green colorblind. Human 3-dimensional color vision, which we call trichromacy, matches the 3 spatial dimensions we experience by complete coincidence. By contrast, many birds, reptiles, and fish have 4 distinct cone types. Their tetrachromacy gives them access to a 4th color dimension and lets them separate hues and regions of the spectrum that blur together for us. At the far extreme, the mantis shrimp and its relatives can carry a dozen or more receptor types, stretching over a wider range of wavelengths. Though recent work suggests they don't combine those signals into richer colors, they instead use each one as a distinct detector, so mantis shrimp can't actually distinguish colors as well as humans. So I suppose a boring version of 4-dimensional tic-tac-toe is to just have red, blue, and green 3-dimensional boards all in a row. It's not much of a game since X can always win in 3 moves, and now it doesn't even look cool. But things get more interesting if we stop thinking in terms of boards and start thinking in terms of coordinates. If we consider the original tic-tac-toe, we have 2 dimensions, each with 3 possible values. We can write out any move on the board by assigning a number to each row and column, and then write the positions we play as sets of 2 coordinates. From the coordinates, you can recognize a winning group. It's just any group of 3 coordinates where the numbers are all the same or all different. In normal tic-tac-toe, for example, a diagonal is 1, 1, 2, 2, 3, 3, a win where values are all different. A vertical line is 1, 2, 2, 2, 3, 2. The horizontal dimension has values that are all the same, while the vertical dimension has values that are all different. To make a straight line, each coordinate either has to stay the same or cycle through different values in sequence. In 3 dimensions, the same rules hold. We can get wins if all 3 dimensions are different for each piece, if only 2 are different and 1 is the same, or if 2 are the same and only 1 is different. We can do the same with 4 dimensions, and the same rules apply for winning combinations, although it gets a bit harder to recognize whether something is a win just by looking at it, as there are a lot of numbers to keep track of. In this 3-board representation, it can be hard to immediately catch sets that span all 3 boards, for example. But we don't have to use numbers. We've already talked about using colors for the 4th dimension, but we could just as soon use different color patterns in our 3rd dimension, or distinct shapes as our 2nd dimension, and count in our 1st dimension. This actually satisfies our earlier decision to keep our dimensions orthogonal, or in other words, pointing in completely independent directions. Just like moving horizontally doesn't change your vertical position, changing a piece's shape doesn't change its color. They're independent, changing one doesn't change the other. Now, instead of drawing out a bunch of coordinates as positions on a board, we can combine all of the components from each of our new dimensions and get objects that have all the specified properties. At this point, it may look familiar to some of you. As a side note, this does mean that under the hood, a typical video game character creator is just a long list of dimensions. So, the appearance of your Skyrim character is a 47-dimensional coordinate in the space of possible characters. Every characteristic you modify just represents another direction you can go to get a unique result, and all of those attributes can be written out as a long string of numbers, just like you would write out positions on a tic-tac-toe board. Now, did I start looking into how many alleles humans have to compare our dimensionality to that of video game characters? Yes. that I eventually realized that a long detour into a fairly complex genetics question was probably a bridge too far for my video about tic-tac-toe? Also, yes. Maybe next time. Returning to our tic-tac-toe board, let's try using colors, patterns, and shapes instead of X's and O's on a board. Using the mapping we defined earlier, our 4-dimensional tic-tac-toe board turns into the 81 cards of a game you might already know. Set, a game designed by geneticist Marcia Falco in 1974, which became popular when it was published in the early 90s. In Set, players race to find groups of 3 cards where each of 4 features, number, color, shading, and shape, are either all the same or all different. For example, if 3 cards all have different numbers, but share the same shape, shading, and color, that would be a valid set. This all same, all different dichotomy should sound familiar. It's the same rule we follow for finding 3 in a row in tic-tac-toe. For example, this set of striped ovals would correspond with this winning row. The mechanic has changed from placing pieces to finding lines from the pieces that are randomly dealt out, but the geometry is identical. Finding a set is just finding 3 points that form a straight line in 4-dimensional space. Well, almost. There's a slight difference in the geometry that I'll have to explain in a minute. But first, let me make sure that we understand the exact mapping between the card characteristics and our grid position. The vertical axis is now our count from 1 to 3. The horizontal axis is our shapes, diamond, oval, and squiggle. And the depth axis is our fill patterns, either solid, striped, or empty. Like before, we can set up different colored axes side by side for our 4th spatial dimension to make it easier to visualize. Now, we deal out 12 cards at random and use the characteristics on each card to fill in the corresponding position on the board using the mapping we just defined. Each player wants to be the first to spot cards that satisfy a set, which is the equivalent of finding 3 in a row on our tic-tac-toe board. In many cases, visualizing the game state this way can make spotting a set much easier than it is with cards. The cards essentially act as camouflage, obscuring the straight lines of the underlying geometry just enough to make the search a challenge. But like I mentioned before, there is one additional wrinkle that we have to consider here. In tic-tac-toe, when values are all different in a dimension, they also have to appear in sequence to make a straight line. In Set, that sequential requirement is dropped. A group still counts as a set even if those differences aren't ordered. This is a trade-off, but it comes with an important benefit. Shifting to simultaneous play removes the first move advantage for X, which we saw amounts to a near guaranteed win in 3 or more dimensions. So while 4D tic-tac-toe might sound like a game reserved for Star Trek, there is a camouflaged version of it that's been sitting in game cupboards for decades. We just call it Set. And with cards, it's easy to imagine pushing this game into 5 or 6 dimensions, just add another independent feature. We can change the color of the background for each card to be white, gray, or black, or include vertical, horizontal, and diagonal orientations. In card form, it's easy to imagine what this would look like. You just add new groups of cards with additional properties. You'd end up with 243 cards in your 5-dimensional game and 729 in your 6-dimensional game. I must confess that I did not animate what the equivalent in spatial dimensions would look like. I have a hunch it would mostly look like an unintelligible jumble of lines. Please feel free to express your profound disappointment in the comments. A big thank you to those of you who stuck around till the end of the video. I also want to shout out Mark Evanstein and his music.py channel. He did a few videos on tic-tac-toe a few years ago that were pretty popular and I think subconsciously probably influenced my decision to make this video. My next video will be about space again, and it's a little more ambitious, so it might take me some time. But until then, I'm analyzing everything.